Oh. Wow. So the heavy, dense carbon dioxide that's been collecting in here, sublimating, walks down the stairs, metaphorically, starts to fill up from the bottom, and puts the candles out. Now, if we filled this room with carbon dioxide, we'd all go out. But that doesn't make for very exciting TV. We're not going to do that. Now, if we did this again and put a little bit of water in here, it's going to generate a water vapor cloud, which is also heavy. And you'll be able to see a little bit better how a dense gas works. So we're going to light these again. Maybe. All right, we'll put the window back on. And then as Kelly slowly pours, watch how the water vapor goes down. And then as the CO2 builds up, it puts the flames out. And that's how the carbon dioxide is working. So now as I move this, you'll see that heavy cloud fall out. Remember, that is water vapor with CO2 in it, not just carbon dioxide by itself, because we can't see carbon dioxide. So that's how carbon dioxide works. The gas that we're exhaling all the time, and the gas that plants need to exist. Thank you, Kelly. Now, we put some carbon dioxide, like this, in our balloon. Something has happened. Connor, come on up and let's talk about what happened in here. So the carbon dioxide has been sublimating. It's a lot bigger than it was, isn't it?
Yeah.
And if you hold it by the top, there, because I don't want you to freeze your hand, drop it on the countertop. It's a little heavier than a normal balloon. And that's because carbon dioxide is so dense. We don't exhale just carbon dioxide. We also exhale nitrogen and other gases. This balloon is just full of carbon dioxide. Now what we're going to do with that is some experiments with liquid nitrogen to show what happens when gases get cold. So I'm going to pour a little liquid nitrogen in here, and Connor, tell them what it looks like it's doing.
It's like it's boiling.
It does look like it's boiling. It is boiling. Now, if you remember from the beginning of our talk, I told you that we do not use the hydrogen and oxygen and gas that were in here in a gas phase. We use them in a liquid phase. That makes them a cryogenic material. That's what would go in this tank, would be liquid oxygen and liquid hydrogen. This is liquid nitrogen. Nitrogen is the primary component of the air we're breathing. So what we've done at the Academy is we have a machine that takes in the air, filters out the oxygen, and then condenses the nitrogen down into a liquid over time. If you're at home by yourself or in a safe place, if you open your mouth and exhale in your hand, or you can see my mask gets foggy, I'm exhaling hot, wet gas. If I do it with my lips closed, you shouldn't see as much condensation build up. That's because when you purse your lips, you've compressed that gas and cooled it down a little bit. That's basically how that process works. And that's how we get those to be cryogenic, or liquids. Now, liquid nitrogen is about 300 degrees below Fahrenheit, about 200 degrees below centigrade, very cold. Now, Connor, if you want to take your hand, put it in here. Just don't touch the liquid.
Cold.
Really cold.
Yeah.
Actually feels kind of nice, right?
Yeah.
A little hot in the studio today. So very cold. Like I said, about 300 degrees below Fahrenheit, 200 degrees below centigrade. What happens to molecules when they get really cold? Now, if anyone knows, absolute zero is 273.15 Kelvin. That's where all molecules are supposed to stop moving. We're not going to get that cold because it's heating up and it's going to, well, the temperature is warming up. We're going to take this balloon and show you what happens when molecules start to get really cold. So as Connor's lowering it in there, the balloon is completely changing. All the gas looks like it was gone and then comes back. Weird. Now remember, this that we see down here is condensed water vapor. Yes, we have water in the air in Colorado, believe it or not. Let's try that one more time. So what happens to those molecules when they get really cold? They don't move very fast. They move really slowly. Now as they start to warm back up, they're moving faster and faster and faster. So in theory, on Monday, it's supposed to be kind of cold around here. So when you go outside and you think, oh, it's cold, I want you to change the way you're thinking and say, it's just the average velocity of the molecules is really slow today. Right? I mean, that's what's happening. Now, it's kind of warm outside today in the sun, and that's the molecules moving really fast, hitting you and transferring their energy to you. You think of that as heat. Your body transmits that message to your brain as heat is being given to you when it's just energy being transferred. Now, something to keep in mind when working with cryogenics is how they're going to affect your rocket. So when the space shuttle main engine was designed, they had to account for the temperature difference they were going to be going through. Feel the flower, Connor. How does it feel?
It's soft.
It's soft. And our cheeks are soft. Aren't we soft?
Mm-hmm.
Why is that?
I don't know.
Do you remember?
No.
Water. So water makes the flower soft. Water makes us soft. Little bags of water, big bags of water. And what happens when water freezes? Turns to ice, right? Now, if we put this flower in your refrigerator freezer for about a day or so, it might freeze. We're going to do it in about 3 seconds. Now, if you notice, I'm not going to touch this flask of liquid nitrogen with my bare hand, because it'll stick onto the beaker, just like your tongue on a wet metal pole in the cold. Bad idea. So I'm going to freeze this for 3 seconds, bring it out, and you're going to clap on it. With some enthusiasm. 1, 2, 3. Give it a clap. Broke the whole flower. How does it feel?
Cold.
Yeah. So it feels kind of nice because we're kind of warm in here. But it feels like frozen potato chips, really small ice chips. And you might be thinking, well, is it going to feel like the flour in a few seconds? Maybe in a minute or two it'll feel like the flour. We're obviously not going to put it back together and make the flour again. So keep that in mind. Because I could freeze his hand and do the same thing, but he'd be stuck like this. I don't think that would be very good. Thank you very much, Connor.
Yeah.
I'm going to tidy this out and move my nitrogen out of the way. And then we're going to do another cool experiment. 5 minutes, thank you. Kelly, come on up.
Yeah, Captain.
So what we have here is a whole different kind of reaction. What we're going to look at now is something called a hypergolic. I'm going to bring my shuttle back up again. If you can imagine, the shuttle is in low Earth orbit, okay? So pretend that the solid liquid tank is gone and the solid rocket boosters are gone. We're talking about just the shuttle. It's flying in a low Earth orbit, and it doesn't just stay there by magic. They have to make corrections all the time. So how are they going to do that? On the shuttle, not to scale, you'll see some little nozzles up here. Those are where they're going to fire thrusters. And that's how they're going to make altitude and attitude adjustments. They can't use the main engines anymore because they don't have any fuel. This has been gone for a long time. So how are they going to do that? They're up in space. There's no oxygen. Nobody's going to hold a match like our lovely volunteer Connor. Terrible job anyway. So we have to come up with another way to get those thrusters to light. We're going to use something called hypergolic. That's a German word for quick igniting. So two substances are going to touch and they're going to ignite. And we're going to produce hot gases really quickly, which is really important for rocketry. Kelly, if you would put 5 drops on there for me, please. Or a little more, it's okay. No, it's all good. So what we have here is a substance called glycerol. What we have here is potassium permanganate. The potassium permanganate has the oxygen built into it, if you can see the formula. And the glycerol is going to provide the fuel. So we have a fuel and we have an oxidizer. And you can see it's starting to smoke. And I'm going to cover this to contain that smoke a little bit. And as it keeps going, it's actually going to ignite. This reaction does not need oxygen from the surroundings to go. The oxygen is being provided by the chemicals. So it's kind of hard to see in there because it got kind of sooty really quick. But because it doesn't need oxygen, the minute the oxygen was gone in there anyway, the system kept going. So they can use this system over and over again. All they have to do is release the amount that they need, shut it off, and it doesn't burn anymore. So this is called a hypergolic system, and this would be something that could be used in space. This particular set is not used in space, but we're not going to bring those kind of chemicals out. This is just a close copy. Thank you, Kelly. All right, our last one is a really cool example of another rocket fuel. This one is the catalytic breakdown of a monopropellant. Come on up, Connor. What we're going to do here is we're going to decompose hydrogen peroxide. This is also known as elephant's toothpaste, even though I don't know why. So Connor, what we're going to do is take some peroxide. This is stronger than the 3% you can find in your store. This is 30% peroxide. I'm going to pour this in here. We're going to add some dish soap because dish soap is really good at trapping gases. And because we don't want this to launch into their ceiling. It's not really as much fun that way. What I want you to do is hold this in your right hand as your pouring hand, right?
Yeah.
You're going to pour it quickly and carefully in there and then just set it down.
Okay.
Are you ready?
Yeah.
Go ahead. Perfect. Now, Connor, if you feel over the top, what do you feel?
Hot.
Hot. Hot gases really quickly. Water vapor. Now, the bubbles are trapped oxygen, and that oxygen is going to find its way out over time. But we've generated hot gases really quickly. This is used in some rockets, like the Soyuz today, to fuel their turbo pumps, but not so much for rockets as they go out to space, not as a primary fuel. So thank you guys very much for your time. I hope you learned a little bit about chemistry fun and some rockets. Hopefully we'll see you in the future.